Across the global network of observatories, a single line of data flashes red. The interstellar object known as 3I Atlas has shifted course, its first deviation since entering the solar system 2 years ago. Initial reports from Pan-STARRS in Hawaii, followed by confirmation from the Atlas survey and ESA's Gaia, reveal a measurable inward drift, several thousand kilometers off its predicted path. Not an error, not a glitch. The numbers hold. Telemetry overlays show the trajectory bending slightly toward the inner system, defying all expected gravitational models. Analysts verify, recheck, and release emergency updates to the minor planet center. Within hours, sky watchers and institutions around the world lock onto the same result. Something has altered 3I Atlas's motion, subtly, precisely, and without an obvious source. If the path correction wasn't caused by nature, the question becomes unavoidable. What force redirected it, and why now? The first detection of the anomaly came quietly, flagged not by a spacecraft but by a ground-based survey in Hawaii. On October 2, 2025, the Pan-STARRS 2 telescope logged a faint displacement in the position of 3I Atlas, only a few arcseconds off its expected track. At first, it looked like a routine measurement error, an alignment issue, perhaps a calibration drift. But as the data accumulated through the night, the offset grew. By the next observation window, the difference had crossed the threshold for statistical noise. The Atlas survey confirmed the shift within hours, and by dawn, teams at the Minor Planet Center had issued a provisional alert. The European Space Agency's Gaia DR4 parallax data offered independent verification, 3 separate instruments, 3 independent calibrations, all pointing to the same offset. Analysts at JPL Horizons recalculated the orbital parameters, updating the official trajectory by less than 0.01%, but with a distinct inward bend. The derived delta V was small, roughly 2.8 plus 0.4 millimeters per second, yet in interstellar dynamics, that is no trivial adjustment. Cross-checks for instrumental bias, plate scale distortion, and atmospheric seeing effects ruled out local error. Even the faintest timing mismatch would have produced random scatter, not the coherent inward drift observed across stations. The conclusion was reluctant but unanimous. 3I Atlas had changed its course, and if the data were clean, that meant a physical force, subtle but real, had acted upon it. For planetary dynamicists, that realization carried weight beyond astronomy. Even a millimeter per second change in velocity, sustained over weeks, compounds into thousands of kilometers of positional drift. In orbital terms, it is the difference between prediction and surprise, between a known trajectory and an unknown visitor cutting deeper toward the sun. It was no longer a question of detection, but of control. To understand that force, astronomers compared what should have been a clean outbound trajectory with what actually appeared on the sky. Before the anomaly, 3I Atlas was following a clean hyperbolic trajectory, typical of an interstellar object making a single pass through our system. Its eccentricity measured near 1.23, inclination 31 degrees, and a predicted perihelion distance just inside the orbit of Mercury at 0.42 astronomical units. Simulations run by JPL Horizons and ESA's Solar System Dynamics Group projected a steady outbound path unaffected by any gravitational encounters after early October. But the newest astrometric data told a different story. When plotted against the pre-deviation model, the object's path showed a measurable inward drift, only a fraction of a degree, but enough to shift its future perihelion by over 20,000 kilometers. At interplanetary scales, that represents an injected momentum change beyond what solar radiation pressure alone could account for. Analysts revisited the usual suspects: gravitational perturbations from Mars, solar tidal effects, and the Yarkovsky thermal drift. None fit the numbers. The deviation remained directional, consistent across multiple epochs, and statistically significant at the 5s level. The pattern hinted at a low, continuous force rather than a single impulse event. Its persistence over several observation windows suggested an origin internal to the object itself, perhaps asymmetric outgassing, perhaps something less ordinary. If no instrumental or gravitational explanation fits, only one question remains. What forces could generate this level of course correction in open interplanetary space? The first and most conservative interpretation points to non-gravitational acceleration, a familiar phenomenon among comets. As sunlight heats the nucleus, volatile ices sublimate, producing jets that act like miniature thrusters. For 3I Atlas, the working assumption was that asymmetric outgassing might be producing a steady push, tilting the trajectory inward. Yet the numbers resist easy classification. At its current distance from the Sun, about 1.7 astronomical units, the thermal flux is low, limiting the rate of sublimation. Standard comet models predict recoil accelerations 1 to 2 orders of magnitude below what was measured. Even when factoring in carbon dioxide or carbon monoxide jets, the energy budget comes up short. Researchers at the Comet Interstellar Consortium, comparing the event with 2I Borisov and 1I Oumuamua, noted that both prior interstellar visitors exhibited subtle but measurable accelerations, though at closer solar distances. In each case, outgassing provided only partial explanations. For 3I Atlas, with no confirmed coma or jet structure visible in high-resolution imagery, the thermal model strains credibility. Alternate natural forces were tested: solar wind pressure, radiation drag, and rotational torque. None aligned with the observed vector. After exhaustive modeling, a small residual delta V remains, unaccounted for, persistent and directionally consistent with an inward correction. The scientific consensus stops there. Beyond that point, only hypotheses remain, waiting for the next wave of data to confirm whether this motion is natural or something else entirely. Following confirmation of the course deviation, telescopes around the world and in orbit pivoted toward 3I Atlas. The James Webb Space Telescope's NIR SPEC instrument secured 2 observation windows before the object's approach to solar conjunction. These spectra revealed a modest increase in reflected near-infrared brightness, about 0.2 magnitudes higher than the previous month, suggesting a temporary change in surface reflectivity. At the same time, the Very Large Telescope in Chile captured narrowband photometry, indicating a shift in the color index from slightly red to neutral gray. This would normally correspond to fresh surface exposure, perhaps from minor venting or crust fracture. Meanwhile, archival imaging from the Transiting Exoplanet Survey Satellite, TESS, though not designed for deep sky objects, provided valuable background photometry. When its frames were stacked, analysts noticed subtle light curve modulation, repeating every 8.3 hours, possibly marking the object's rotation. The amplitude of that modulation appeared to grow in October, hinting that one hemisphere had brightened more than the other. The mystery lies in the chemistry. Despite the photometric brightening, JWST and VLT both reported no significant gas emission lines, particularly the carbon-based features expected from active comets. An apparent rise in albedo occurred without corresponding signs of outgassing or plume formation. If the surface changed, it did so quietly, without the usual spectral fingerprint of volatiles escaping into space. For many, that paradox deepened the intrigue. How could an object grow brighter, yet remain chemically silent? By mid-October, 3I Atlas slipped behind the Sun from Earth's perspective, entering what astronomers call solar conjunction. During this period, the line of sight between Earth-based instruments and the object passes dangerously close to the solar disk, saturating detectors and blocking most radio transmissions. For roughly 6 weeks, the object would remain hidden in the glare, an unavoidable blackout window in planetary observation. Agencies prepared for the gap. The Minor Planet Center, NASA's Planetary Defense Coordination Office, and ESA's Near-Earth Object Coordination Center issued synchronized bulletins confirming the hiatus. All positional updates beyond October 17th would rely on projected models until visual reacquisition in early December. But the silence carried consequence. Without fresh data, public speculation filled the void. Amateur astronomers debated online whether the inward acceleration had continued. Some claimed early Mars orbiter images hinted at a faint tail extension, claims unverified and unendorsed by any mission team. Data latency worsened the tension. Normally, raw image archives from JWST and VLT appear within days. This time, releases lagged for weeks, pending additional calibration. Agency spokespeople cited necessary corrections for solar interference and radiation noise. Critics, however, questioned the delay's length. Inside research teams, scientists held their breath. With the object receding deeper into the Sun's glare, any unobserved event, a fragmentation, a burst of jets, or a full stabilization, would remain invisible until December. The countdown began. When 3I Atlas reemerges, would it return on its predicted curve, or on an entirely new path? This phase of analysis remains openly hypothetical, focusing on forces that might explain the residual acceleration, not accounted for by solar or gravitational effects. The leading natural model involves outgassing asymmetry, localized jets venting on one side of the nucleus. Computer simulations by the Comet Interstellar Consortium suggest that even small regional vents could create a net thrust if they remained active over multiple rotations. The problem is evidence. No jets have yet been imaged. Another possibility still within mainstream physics is mass redistribution inside the object. If internal cavities collapsed or shifted, the resulting momentum transfer could subtly redirect motion. Such internal events have been observed in long-period comets, though never in one traveling at interstellar velocity. More speculative proposals, not yet peer-reviewed, involve magnetic coupling between charged dust grains and the solar magnetic field. This could, in theory, impart measurable acceleration under the right plasma conditions, but the model requires densities far higher than those detected. Beyond these are the fringe hypotheses, suggestions of deliberate or engineered maneuvering. These ideas circulate primarily in non-academic forums and remain unsupported by any empirical data. As researchers emphasize, no evidence currently confirms artificial control or intelligent design. For now, the scientific verdict is restraint. Until 3I Atlas reappears and new spectra arrive, every explanation, natural or otherwise, remains only a hypothesis waiting to be tested against the numbers. By late October, the official response to 3I Atlas's deviation was fully mobilized. The Minor Planet Center released 2 rapid circulars confirming the updated orbital elements, marking the object's revised trajectory as provisional pending further astrometric recovery. Within hours, the Planetary Defense Coordination Office, PDCO, at NASA, began coordinating with the Jet Propulsion Laboratory's Solar System Dynamics team and ESA's Near-Earth Object Coordination Center to refine the new ephemeris. Inside JPL, recalibration teams used Gaia and Pan-STARRS photometry to synchronize positional data, correcting for parallax shifts and timing offsets between observatories. Publicly, Dr. Lena Kovacs, a planetary dynamicist at JPL, addressed media inquiries emphasizing the need for patience. The data are sound, but interpretation takes time. Even small deviations must be verified across multiple instruments before conclusions are drawn. ESA's Science Operations Center released its own statement, confirming the integrity of the Gaia measurements while noting the importance of cross-matching with radar data once the object re-emerges from conjunction. To maintain transparency, NASA and ESA agreed to publish a joint database of all 3I Atlas observations under an open access policy, including calibration files and astrometric corrections once the blackout ends. Still, behind the scenes, tension remains. The drive to release results quickly competes with the need for precision. Each dataset must be peer-reviewed, each photometric correction checked twice. In every lab, the question hangs unspoken. When 3I Atlas returns to view, will the new trajectory confirm the models or break them again? The next opportunity to track 3I Atlas begins in early December 2025, when the object re-emerges from solar conjunction. A global observing campaign is already in place. The James Webb Space Telescope has reserved a mid-infrared slot between December 9th and 12th, aiming to capture thermal emissions at wavelengths sensitive to dust and gas. This will help determine whether residual outgassing is still occurring, or if the object has stabilized. Simultaneously, the Vera C. Rubin Observatory's LSST will conduct its first wide-field sweep of the object since the deviation was recorded. Its high-cadence imaging will refine astrometric data to within fractions of an arcsecond, providing the most accurate orbital measurements to date. Teams at Goldstone Deep Space Communications Complex are also preparing radar experiments. Though detection remains uncertain at such distances, the campaign will compare every data point against pre-October baselines, brightness, spin rate, and any residual acceleration. Small differences in trajectory or photometric variability could confirm whether the inward drift continues. Scientists emphasize that this phase is not about speculation but confirmation, verifying with precision the physics behind the anomaly. In effect, December becomes the system's next test. If 3I Atlas's motion remains consistent with natural models, the case closes. But if the deviation grows, even slightly, new questions will follow. Questions that reach beyond orbital mechanics into how interstellar objects interact with our sun, and perhaps with forces we do not yet fully understand. After months of analysis, 3 facts stand beyond dispute. First, 3I Atlas, an interstellar visitor traveling on a hyperbolic path, experienced a measurable course deviation in October 2025. Second, every independent dataset from Pan-STARRS to Gaia confirms that the shift was real. And third, no known gravitational or instrumental effect can fully account for it. Everything beyond that remains open. Theories range from asymmetric outgassing to internal mass movement, with some speculative models invoking magnetic interactions or untested plasma effects. What matters now is evidence. Scientists across the world are preparing for the December reacquisition window, where every pixel and photon will decide which explanations survive. In many ways, 3I Atlas has become more than a celestial visitor. It is a probe of our own understanding. If its course change proves natural, we may uncover new physics governing how interstellar materials respond to solar energy and magnetic fields. If it is not, the implications extend far beyond cometary science. Until then, the data stand as both a warning and an invitation. In the space between what we know and what we can prove lies a single unanswered question. What exactly acted on 3I Atlas as it crossed our system? The next light it reflects and the next spectrum we record may hold the answer.